Hi there. The latest addition to my lab arrived straight from China in the usual plastic bag. It's the OWON XDM1041, which is still fairly new on the market and not the easiest thing to get. Is it any good? For your 110 pounds or about $160, do you get a lemon or a peach as a multimeter? Let's find out. In the box we have a proper UK power cord, which is what I selected when ordering. Some add-on alligator clips for the probes. A good old standard RS-232 serial cable, nothing of that new-fangled USB rubbish here. A pair of probes. And finally, the meter itself. And some documentation. You notice that for a bench meter, this one has a very unusual form factor. After connecting power, a long press on the power button starts the meter. And about 6 seconds later, it is ready to measure. I like the large display, easy to read, and although it's not very noticeable in this shot, the slight upward tilt of the front is perfect for viewing when the meter is standing at the rear of a work table. At the back we have just the RS-232 port on the left and the IC power socket on the right, so no voltage selection is necessary. It works from 90 to 240 volts AC. The IC power socket has an integrated fuse holder, and with a bit of persuasion the fuse can be extracted. It is, as the label on the rear suggests, the type F1AL 250 volts, a common one for small appliances, a fast-acting 1 amp fuse with low current breaking capability. Continuing the journey into the meter, I removed the only visible screws, the 3 at the back. They are all self-tappers and very deeply set in their respective holes. There are 2 additional screws hidden under the rubber feet, which can be simply slid backwards, and once they are out, the housing comes apart easily. In the lower left, we have obviously the power supply board, and on the right, the tiny board for the serial interface. Interestingly, the communication seems to go through the power supply board. You can actually see the traces on the PCB. In the top we have the multimeter part, which is actually a sandwich of 2 boards, but not easy visible here. And finally, on the left is the back of the LCD display. Let's start with the power supply. It looks spacious and fairly well made. We have a fusible resistor, a varistor, and a suppression choke at the input, followed by the high voltage caps. The rectifier must be on the underside. They even put tracking slots in to separate the live, neutral and ground pins. We have a nice looking transformer and the usual arrangement of Y capacitor, which is a properly rated one by the way, smoothing caps and another choke to filter the output. A nice touch is the silkscreen print here. So this is a single output 5 volts 2 amps power supply. Obviously this makes it very easy to convert this meter to USB or battery powered if you wish. They went through quite some effort for good isolation on the secondary side of the transformer, not something you see very often. Let's see if the good impressions carry on to the underside. The board is held with 4 screws and can be easily lifted out and flipped over to inspect the underside. The separation zone between high and low voltage runs here and is ample. It may look as if this trace from the low voltage goes to the mains connector, but I checked it stays well clear of live or neutral and goes to the ground pin instead. You can see that the 2 connectors carry 5 volts and ground with nice fat traces, and the other 3 ones are just receive, transmit and data ground going from one to the other. As suspected, the mains rectifier is here, and the switching is done by a on-bright chip of the OB2536 series. The very tip of it you can just make out here. It's a pretty standard design as you would expect. I've seen a lot worse power supplies than this one. Maybe one thing to mention What isn't here is any sort of mains power switch. This means this power supply is always on, as long as mains is plugged in. And one thing to check is the power consumption in standby. Moving on to the actual multimeter part, which is, like in many bench multimeters, split between separate analog and digital boards. In this case, sandwiched one above the other. The digital board is below and the analog one on top. They are separated by a hard-to-see transparent sheet of plastic for isolation. The big black box you see is actually an isolated DC to DC converter next to a couple of opto-isolators. The analog board is completely isolated from all the other boards, and the interface to the rest of the multimeter is just this corner. You can see the isolation slot for the DC converter and the opto-isolators. The actual measurement is done by this dedicated chip, a HiCon HY3131, which is the same chip Dave Jones of the EEV blog uses in his 1-to-1 GW multimeter, and I'm happy to see it in this multimeter too. The datasheet of the HY3131 says 50,000 count, while the XDM1041 says 55,000 count. I guess they include the little overshoot that is usually there to deal with the auto range, something to check later. Anyway, without going into details, this chip contains a lot of good stuff, including the usual measurement ranges, true RMS, a slower high-precision 24-bit ADC and 2 faster 19-bit ADCs, voltage reference, digital filters, frequency counter, peak hold, and so on. Before moving on, 3 more things to mention. These are the backs of the input terminals, directly soldered into the analog board. Maybe not the world's greatest solution, but okay I guess. There are quite a number of tracking slots cut into the board to improve creepage distances, which shows attention to detail. But annoyingly, they saved a few pennies by soldering in short fuse holders, even though the PCB has provision for decent 30mm long fuse holders for 1000 volt rated fuses. Nothing I cannot fix myself, but it's sad that I have to. So let's have a look at those fuses. The ceramic one is a 250 volts AC 10 amp job, labeled HD500 and made by Disman. I know that Busman is a well-known maker of quality fuses plagued by cheap fakes and knockoffs. Is this one of them? But apparently no. Disman exists in Shenzhen and have all kinds of impressive certificates and approvals. Sadly, their search function is a bit broken, so I wasn't able to find the specs of my HD500 fuse. My guess is that it's a fast-acting 10 amp fuse, at least it should be. The second fuse is of the glass kind, and I'm always a bit wary of applying a lot of force, as some can break easily. Anyway, I got it out at last, and it's an unbranded 1 amp fast fuse for 250 volts. This should be a 600 milliamp fuse, the manual even says so. The first thing that needs fixing. It's disappointing to see that all the other good safety work is ruined by saving a few pennies on fuses. With the cheap fuses restored, at least for now, it's time to investigate the underside of the analog board and to have a look at the digital one. It is possible to fold the analog board to the right without the need for unplugging. One of the sockets remained attached to the housing, but that's okay. It is hard to see, but there is actually a transparent sheet of plastic as a separator and isolator between the analog and digital board. You can just see a corner of it here. The first thing that catches the eye is the unusual flat 10 amp current shunt wire, which is covered in some isolation material. Probably a normal standing shunt would be getting too close to the digital board, and they also want to protect the transparent isolation sheet from the heat of the shunt. The big chip across the isolation slot here, separating the analog board from the rest of the meter, is a NovoSense NSI 8141W0. A high reliability quad-channel digital isolator for the high-speed communication of the HiCon HY3131 with a digital board. It has 3 channels in one direction and 1 in the other. Next to it is the regulator for the 3.6 volts feeding the HY3131 on the other side. On the right we have 2 relays, probably these are driven by the opto-isolators we saw earlier. Then, to get the 1000 volt rating, there is this chain of 4 times 1.5 megohm resistors in series coming from the volt input terminal. Building a large input resistor that way improves the voltage rating, and they add isolation slots to avoid any creepage. Nice! On the far right we see the one and only varistor for protection, which is a bit mean but better than none. And further up there's obviously some clamping. On to the digital board. Not too much going on here. There's the brains of the multimeter, an ARM-based 32-bit microcontroller from Giga Device, the GD32F303CCT6. The controller can use a battery to preserve backup registers and to keep a real-time clock going, and by the looks of it, this is what OWON has implemented here. The battery is a rechargeable 3 volts MS621FE cell, and according to the datasheet good for 1000 cycles at 20% discharge. It is soldered in, so replacing means some effort. Further up we have the voltage regulator for the microcontroller. And then there is this 8-pin chip here, which I was unable to find any information about. If anyone can identify it, please leave it in the comments. Time to put the digital and analog boards back together, including the clear plastic separator. Last not least, the smallest of the PCBs, the serial interface. There's not much going on here. The DB9 serial interface connector is directly soldered into the back. The board gets 5 volts and ground, as well as TTL compatible serial signals from the digital board via the power board. The chip is a SP202E, which converts TTL signals into proper RS232 signals with the right positive and negative voltage levels using built-in charge pumps. It implements 2 transmitters and 2 receivers, but the second transmitter-receiver pair is not used by this board. Before closing, one more test. I measure continuity from the earth pin of the mains plug. As expected, it appears on the power supply board because it's actually connected to the ground of the 5 volt supply. Therefore, the RS232 connector and ground is connected, and so is the digital board. But the analog board and its terminals are free floating. The black ground terminal has no connection to the mains ground. This is good and quite important for safe measurements using a mains powered multimeter. And speaking of mains powered, let's see what the meter draws from 230 volts mains. When operating, the current is around 12.5 milliamps, which would be just below 3 watts. And once turned off, which is really just standby, the current sinks to about 1 milliamp, which is around 1/10 of the operation current. I would prefer complete power off instead of standby, but less than 1/4 watt is tolerable and it keeps the soldered in backup battery charged. How many counts does it actually have? It claims 55,000 as you can see, but we know the DMF chip says 50,000. As you can see, it does indeed go all the way to 55,000 and then switches range. But the way it does it is weird. Let's see that again in slowed down. It first tries 500, he gets a reading, sees that 50 would be better, and settles on 50 volts. Well, it gets there in the end, but since the meter is rather slow, in slow mode at least, you need to wait. On the way down, it keeps the 50 volt range as expected until we drop below 5 volts, then it switches back to 5 volt range. To finish this part of the review of the XDM1041, let's have a look at what else came with it, starting with the probes. They are of decent length, 1.1 meter tip to tail, and of medium quality, no shrouds for the tips but reasonably sharp. The alligator clips fit on the probe tips but not very tightly, so the probe can easily be pulled out accidentally, and contact resistance is another question. The isolation hinders the operation considerably, convincing me never to use this anyway, but some folks may find them useful. The alligator clips are rated 1000 volts Cat 2. The probe themselves 1000 volts 10 amps Cat 3, but the meter is only Cat 2, and even that seems a bit doubtful given the fuses. Limit yourself to Cat 1 and 250 volts to be safe. The leads themselves have a rating too, which is a surprise. 0.35 mm PVC rated for max 105 degrees and 1000 volts. I take the 0.35 mm as 0.35 mm squared, that is the area, which is kind of matching what my measured resistance of about 65 milliohms for one lead is. Rather thin for 10 amps, better use decent leads for higher current. The RS-232 cable is 1.4 meters long with 2 dB9 female plugs at the ends. It's a straight through cable, no swapping of TX and RX, and only pins 2, 3 and 5 are connected, which is what you would expect from the interface chip in the meter. The documentation consists of a spec sheet and a small booklet on operations of the meter. Both were in English without any other languages added and actually quite well written, but still probably a bit on the short side for anybody completely new to multimeters. I found an OWON site in Hong Kong where you can download the XDM1041 manual and spec. I leave a link in the description. And there's a spare fuse, another 1 amp no-name type meant for the power supply. So far we have looked at the hardware of the XDM1041 and overall I quite like it. A few issues like the cheap fuses and probes can be fixed, but there's good attention to detail and it's well constructed. Moreover, there's ample room and opportunity for mods. It would be easily converted to battery power if needed, and because the interface to the analog board appears relatively simple, a 4-wire SPI link and a few discretes for the relays, it might even be possible to add your own processor board if the onboard one can't be reprogrammed. Lots of potential. So definitely on the peachy side for now, but especially if you'd rather leave it as is, wait until you see my next videos on the look and feel of the XDM1041 user interface, its accuracy and remote control interface. So don't forget to subscribe if you not have already, and maybe consider becoming a Patreon, link in the description. As Patreon you get early access to videos, a blog and other exclusive content. Thanks for watching.